afternoon. We're going to get started. So today we're going to talk about some reversible reactions of type 2 carbonyls, and I will let you know the stopping point for Friday's midterm. So I opened up chapter 22 later on this afternoon. I'm going to send you an email telling you the relevant problems from Sapling chapter 22. And I'll also tell you the relevant problems from the end of the chapter for Smith. Okay? Questions, anybody, about upcoming midterm, all of that kind of stuff? No? All right. All right, so here's where we start talking about the electrophilic addition reactions of the reversible. But first, a quick review of the irreversible addition reactions of type 2. That will be very relevant for you for midterm 1, right? So here we have strong nucleophiles. I'm using Grignard as an example here. And here's our generic type 2 carbonyl with the group L. That can be a leaving group, also has a lone pair. We make our tetrahedral intermediate. Oh, let me fix that. We make our tetrahedral intermediate. Irreversible addition, the leaving group leaves. Boom, we kick the leaving group off. And then we have to make a decision about whether the addition is going to happen again, and it turns out that the addition is going to happen again here. Because, well, we don't know. We can't compare reactivity here when we have the generic version, but the Grignard is going to add again. And so we end up getting an alcohol. So this is a great way to synthesize alcohols. So we end up getting the alkoxide. And when we add water in a second step, we protonate. So we'll just put water over here. So that's actually a possible mechanism for midterm 1 that we've already done. All right, so there's our generic example of addition of a reversible reagent. Now here's the deal. For this one here, we have only one leaving group possible, and that's this leaving group L. And that's because this group that just came on can't come back off again as a leaving group. When you use weaker nucleophiles, we're actually going to have a choice of leaving groups. So we have to know leaving group ability. Okay, so here we only have one possible leaving group, L. Down here, when we have these guys, we're going to have other potential leaving groups. So we're going to have to be in a position to make decisions about that. So that's why I want to go into a little bit more in depth on the reactivity of the type 2 carbonyls. We've already talked about one aspect. We did not talk about leaving group ability. So we're going to just do a little bit more in depth here. So here's our reaction here. One more time. No one's going to miss that on the test because I've done it so many times, right? That particular reaction. So a nucleophile attacks the carbonyl. That's addition, which I'll abbreviate add. That's an addition. Here's our tetrahedral intermediate. And then in the second step, elimination, electrons come down and kick off the leaving group. And of course, the overall process is acyl substitution. Now in Smith, they say the rate of the reaction has only to do with the leaving group ability, and that's not really an accurate way of looking at it because the second step depends on leaving group ability. The first step does not depend on leaving group ability, does it? We have to do the first step first. When we look at just the leaving group, we're talking about the second step. We still have to look at the first step, because if the first step doesn't happen, then the second step can't happen. So it's a little bit more of an explanation than that. And that's what we're going to be focusing on in this next part of the chapter. All right, so the rate of the reaction is going to depend on the stability of the carbonyl derivative. That's because of that's going to affect the rate of addition. The first step. Which is step 1. And the rate of the reaction also depends on the leaving group ability of L. That would be for the rate of elimination. The leaving group ability is going to affect the rate of elimination. Which would be step 2. So we may be able to do step 1, but then if we can't do step 2, then it will just go backwards. Okay? So we have to talk about both steps if we're going to talk about the rate of the reaction. So let's talk about the first one, the stability of the carbonyl. We've already done that. We know about the stability of the carboxylic acid derivative, or the type 2. The stability depends on the concentration of positive charge on the carbonyl carbon. And we talked about the inductive effect and the resonance effect to explain that. And so you could go to page 12 to 14 of your notes to do that. I don't need to talk about that again. And here's our order of reactivity that everybody knows for the midterm on Friday, right? So acid chlorides have a strong inductive, which destabilizes, and a weak resonance. Resonance is the thing that stabilizes. Inductive destabilizes, resonance stabilizes. And so that makes sense that acid chlorides are the least stable. Least stable or most reactive. And then we saw carboxylate has the carboxylate anion is the most resonance stabilized of all of these guys. So this is the best resonance. And resonance stabilizes, and so it makes sense that this is going to be the most stable, least reactive. Notice I don't have aldehydes and ketones here because in this particular chapter we're talking about just type 2s. So I left them out entirely. Aldehydes and ketones don't do acyl substitution, so that's why I left them out. All right, so the second thing we need to talk about is leaving group ability. Best leaving groups are weak bases, right? We learned that back in 51A. So this is sort of the adage I told you at the beginning of class. Everything you've learned this year is going to all come back to you in 51C. So that was back in 51A that we learned that. So let's talk about leaving group ability here. So leaving group, how do we measure leaving group ability, weakest base? So we look at the pKa of the conjugate acid, right? So here's our leaving groups. I'm going to circle all of them. Hydroxide, ethoxide, NH2 minus, Cl minus, okay? pKa of the conjugate acid here would be HCl, that's -7. pKa of this conjugate acid, that would be just acetic acid. We know that's about 5. pKa of the leaving group ability of hydroxide, the pKa of the conjugate acid's water, and that's about 15. And likewise, here we have ethanol as our conjugate acid for that leaving group, and that's also about 15. And then NH2 minus, we'd look at the pKa of the conjugate acid, which would be ammonia, that's about 35. So most of these we know rounded to the nearest 5 on those few pKa's that I want you to know, rounded to the nearest 5. So what we can see here is that we have increasing base strength as we go this way. And then in the other direction, we have increasing leaving group ability. So the arrow would go the other way. So notice an acid chloride, that's our most reactive, and it also has the best leaving group. These things tend to work together for the type 2 carbonyls. All right, so let's go back to the rate of the reaction. So the first step is addition. Second step is elimination. If we decrease the stability of the carbonyl, so as that carbonyl, as that type 2 carbonyl becomes less stable, you're going to increase the addition rate, right? The more stable the carbonyl, the slower the addition rate. So that's the first step. And then when we have the second step, this is all about leaving group ability. For elimination, if we increase the leaving group ability, we increase elimination. And so if we have a poor leaving group, that's going to slow down that second step and may not even enable that second step to take place. All right, so I'm going to look at some energy diagrams for the extreme cases. I'm going to start off with carboxylic acids and esters. And they have very similar, they're very similar in their reactivity. Both of these guys have resonance stabilization, and they have some inductive effect and resonance stabilization. But what we're going to say for this class is that this ester and this carboxylic acid are about the same electrophilicity. So they're about the same electrophilicity. And we looked at leaving group ability, and using our pKa's rounded to the nearest 5. These are not exactly the same, but they're about the same, about pKa 15. So energy level, these guys are about the same, so that's why I have them here, right there, and there. That should be at the same energy level, and that's what it's going to look like. And so if you look here, we have energy of activation for the first step is right here, taking the ester and going to a carboxylic acid. Here's the energy of activation for the first step. We have our tetrahedral intermediate is going to be right here in the energy diagram. Let's see what that looks like, what our tetrahedral intermediate is going to look like. All right, so what's going to happen is the hydroxide is going to attack the carbonyl. We're going to give us that tetrahedral intermediate. So we can actually even draw that down here. Let's just draw that down here. Boom, it's going to attack the carbonyl. We're going to kick electrons up onto oxygen, just like we've been doing. And that's what our tetrahedral intermediate would look like. And notice, we have 2 leaving groups now. We have 2 potential leaving groups. So that's what's different about this chapter is we're going to have to choose leaving groups. Both of these leaving groups have about the same leaving group ability. So similar leaving group ability. So this tetrahedral intermediate is going to want to go back to a carbonyl. If this methoxy group comes off, it'll go here. So it starts off here, it will go here. And if the hydroxide comes up, it will go right back to starting material. And because those 2 leaving groups are about the same, we have the same height for this energy barrier here for both of these. So what we're going to have to do is when we're trying to take an ester and convert it into a carboxylic acid, if we don't drive the equilibrium, we're going to get a 50-50 mixture, right? So we will have to drive the equilibrium here. And we're going to talk about that reaction coming up, but we'll just definitely have to drive the equilibrium. So, and that's because the energy of activation of the reverse reaction is approximately equal to the energy of activation of the forward reaction. So therefore, we'll get a 50-50 mixture. at equilibrium unless you drive the reaction. So we're going to have to worry about that when we get to esters and talk about converting esters to carboxylic acids and the reverse reaction converting carboxylic acids into esters. We're going to have to drive the equilibrium. Okay, so that's when the two are about the same. Let's look at it in the second energy diagram. What happens when we have a carbonyl compound stabilized by resonance and containing a poor leaving group? That would be an amide. See what happens here. So here's our amide right here. And we want to try to convert an amide into an acid chloride. All right, so chloride ion attacks the amide. What would the tetrahedral intermediate look like? Let's see. Let's draw the tetrahedral intermediate over here. All right, so we have NH2 here. We have chloride. Very large energy of activation for that first step. Why is that? So large energy of activation. Because amides are pretty stable, aren't they? They have very strong resonance stabilization. Not as strong as carboxylates, but they're very strongly resonance stabilized. Okay, so that's because amides are pretty stable. So when things are stable, they're not going to want to react. So we have a really large energy of activation for the first step. And then if you look at the energy of activation for the second step, once the molecules have enough energy to overcome that first energy barrier, then they have to come up with this much more. Okay, so the molecules have to come up with this much extra energy in order to go to the product. So what's the rate determining step for this reaction? First step or second step? It's the second step, because you need to come up with this, the molecules need to come up with this much energy and this much more. So the rate determining step is the highest mountain to climb there, and that's the highest mountain to climb. So this is so large, this energy of activation 1 and energy of activation 2, that the reaction doesn't happen. And when you draw your tetrahedral intermediate, you can see why this reaction doesn't happen. Which one is the best leaving group here? That's the best leaving group. pKa of the conjugate acid is -7. pKa of the conjugate acid of NH2 minus is 35. So what's the best leaving group? By far, it's going to be chlorine. So what this guy wants to do is the electrons come down and kick the chloride ion right back off again. So in other words, even if you can get this first step to happen, this second step is not going to happen, because we want the best leaving group to leave. We can't have this chloride stay and have this as a leaving group, because this is by far orders of many orders of magnitude better leaving group. So that's why too high of energy. So you can't take an amide and convert it into an acid chloride directly by acyl substitution. It doesn't happen. All right, so this is the best leaving group. So it's easier for the tetrahedral intermediate to collapse back to starting material. So what's going to happen is those electrons are going to come down. So by collapsing back to starting material, I mean these electrons are going to come down and kick that chloride ion right off. So you're going to just go right back here anyway. Okay, so there's another extreme case. Now let's look at the other extreme here, where we have an energy diagram where the carbonyl is very reactive, contains a great leaving group. And this is scrolling all weird on me. Sorry about that. So our best example of that is an acid chloride. We're taking acid chloride and converting it into carboxylic acid. All right, so let's see what that looks like. Hydroxide's going to attack. I put these too close together, but you get the idea. Hydroxide's going to attack the carbonyl here, so this is our tetrahedral intermediate. Let's draw it. What's the best leaving group? Chloride's the best leaving group. That's the best leaving group. And so that's what's going to happen. So best leaving group, loss of this, therefore loss of this leaving group is faster. So it has a smaller energy of activation. If we wanted the hydroxide to leave, then that would be a larger energy of activation. And so we're going to follow the lowest energy pathway here. So we have two things going on here. We've got a great leaving group, so that's going to be a small energy of activation. We also have a small energy of activation for the first step. So this is EA1, this is EA2. So EA1 is small, so therefore we have a fast first step. Why? Acid chlorides are very electrophilic. That's it. And EA2 is also small because we have a great leaving group. Acid chlorides have a great leaving group. Questions on the energy diagrams? Anybody? All right, so what you've noticed is if the reaction goes readily, we have a lower energy product. It's exothermic overall. Over here, this is endothermic. Not going to be easy, right? Doesn't happen. And then we also have where we have similar reactivity in this energy diagram, and those are the ones where we're going to have to drive the equilibrium. Okay, so going uphill is a problem. Going downhill is not. So we're going to summarize these. This thing does not scroll very well. These factors can be summarized, and that's at the top of your next page. So here's our order of reactivity. Increasing stability of the carbonyl. we also have increasing basicity of the leaving group. So the result of that is that if we have increasing stability, then we're going to have a faster reaction rate this direction. Increasing reactivity. And we're also going to have, so that's for step 1, and we also have increasing leaving group ability. And that's going to affect step 2. And this one here is step 2. All right, so that's the reactivity of this reaction in a nutshell, and that's going to actually help you make decisions here coming up when we look at all of these type 2 reactions with reversible reagents. Okay, so what we're going to do is we're going to start with this order here. We're going to start with the most reactive here, acid chlorides. And then we're going to talk about anhydrides, and we're going to talk about carboxylic acids, esters, and then amides. And we're going to do it in that order. So we're going to start with reactivity of acid chlorides. And pretty much it's very easy to take any of the acid chloride and convert it into any of the other type 2 carbonyls. Very easy. So we start here. This is energy level. Here's our acid chloride. And so then these are the various other different energy levels. This is really not to scale, but here we have anhydride, energy level. We have ester and carboxylic acid, so ester and acid. And then we have amide. And it's easy to go downhill. So if we have an acid chloride, you can have the small energy of activation here, and then small energy of activation for the second step. And then likewise, we can go down here easily, and we can go down here easily. If we try to go the other direction, which would be uphill reaction, so if you try to go uphill, you run into a problem. So for example, let's say you try to take an ester, which would be right here, and go to an acid chloride. Large energy of activation for the first step. And the second step would be even larger energy of activation than the first step. So can't go the opposite direction. So we're going to put a big X through that. So in general, less reactive acyl compounds can be easily synthesized from more reactive ones. Forming a more reactive acyl compound from a less reactive one requires special reagents or forcing conditions. I want you to remember that. Special reagents or forcing conditions. So that would be this example right here. And we're going to see both of those types. We're going to see special reagents and we're going to see forcing conditions. All right, so let's look at some acyl substitution reactions with acid chlorides. We can easily make an acid chloride into an anhydride. We would use conjugate base of a carboxylic acid, so it looks like this. So any one of these acid chloride mechanisms is a possibility for midterm 2, but they're all the same. Very much the same anyway. That would be addition. And the problem, if you try to memorize reagents and products, you're going to get completely overwhelmed. If you actually do the arrow pushing, you draw, you look at the tetrahedral intermediate and make decisions about what's going to happen, then it's going to be much, much easier for you. So I really highly recommend that. So let's look here. We have this. What's the best leaving group? Chloride ion is the best leaving group. pKa of a conjugate acid is -7. It's going to come off like a shot. That's really going to be a fast reaction. So here's our best leaving group. And that's what's going to happen in these reactions. Best leaving group is going to win. Best leaving group is going to leave. So then we get elimination, and there we have our anhydride. All right, now let's make an ester from an acid chloride. This is probably going to remind you of the thionyl chloride mechanism from 51B, Chapter 9. I'm thinking so anyway. Remember Ph.D, non-nucleophilic base. Let's draw that. Our favorite non-nucleophilic base from Chapter 9. So imagine that this is thionyl chloride. We're going to be doing the exact same thing. So this is addition. Let's draw the intermediate that we get. All right, what's our best leaving group? So methanol, what if methanol leaves? pKa of the conjugate acid of methanol is protonated methanol. That has a pKa of about -5 or -6. pKa of the conjugate base of chloride ion is -7, so what's the best leaving group? Chloride ion is the best leaving group. And so that's what's going to happen. Best leaving group is going to leave. So are you seeing that the correlation here with the thionyl chloride? We attacked the sulfur, we kicked electrons up onto oxygen, and electrons on oxygen came down and kicked off chloride. Exactly the same here. Second step is elimination. And again, this is best leaving group. Oops. And here's where the pyridine comes in. The pyridine comes in to deprotonate that oxygen. So ester from an acid chloride. Another possible mechanism for midterm 1. All right. Acid chloride plus 2 equivalents of methylamine. We got that 2 there. I want to talk about that in just a second. But let's go through this. We need 2 equivalents here. I know you hate that when we got to worry about 2 equivalents, but you'll see why here, what I'm talking about. So, yeah, this is going to cause a problem. I guess I'll go on to the next page here. So here's addition. Alkoxide. Leaving group. What's our best leaving group? Always chloride ion. How about that, huh? So -7 for HCl, about 10 for ammonium ion, which with the pKa for that amine if it leaves. Okay, so then the second step is elimination. So we've already used one equivalent of amine, and now we need a second equivalent to deprotonate. So acid chloride to amide. All right, so let's take a look here. This is our first equivalent, and here's our second equivalent. Sorry about that. So an extra equivalent of amine is needed in this reaction. Why? CH3NH2 will be protonated in this reaction, and CH3NH3 plus is not nucleophilic. If we don't have a second equivalent of amine in there, then we will protonate the remaining amine and we will only get 50% conversion. Okay, so reaction will stop at 50%, so that's the problem with that one. So why not just deprotonate with the chloride ion generated in the reaction? That's really not going to help us anyway, because if we deprotonate with chloride ion, we'll form HCl, and what's HCl going to do with the remaining amine that's in there? Just going to protonate it, right? So just going to protonate it. So let me show you what I mean here. So we do the addition, we get to this point, you say, okay, why do I need excess amine? I can just do this instead. Deprotonate with chloride ion. There's my base. And of course, if you do that, you will produce hydrochloric acid. What's the fate of the hydrochloric acid? Well, it's going to react with the amine here. I'm going to do long arrow to the right, short arrow to the left, and we're going to prove that. We have that, plus we have Cl minus. So we look for our acid on each side of the equation. Hydrochloric would be here on this side, and the protonated amine would be our acid here. And we look up the pKa. This is pKa minus 7, and this is pKa about 10. So at equilibrium, we have one hydrochloric acid for every 10 to the 17th protonated amine. So it really doesn't matter what we use. We do need either two equivalents of amine, or there's another thing that you can do, and we did this back in chapter 18. And I'll just draw it right up here, and you can draw it in the margin of your page. You can also use one equivalent of amine and one equivalent of pyridine, a non-nucleophilic base. Instead of two equivalents of amine. All right, so remember from last quarter, if you had me last quarter, if you don't, it doesn't matter. I'll show you right now. Remember from last quarter, when we had aniline, and we ran into all sorts of problems with aniline last quarter when we were trying to do electrophilic aromatic substitution. And so a solution to many of our problems with aniline was to take aniline and convert it into acid anilide. Remember that? Is it all just running back to you here, hopefully? We had that and pyridine, right? We made acid anhydride, and acid anhydride is much more well behaved in an electrophilic aromatic substitution. So that's what this reaction is. I promised you we would be covering it this quarter, and there it is. And we'll be doing the mechanism for that in discussion this week. Okay? Questions on reactions of acid chlorides? Anybody? Okay, and so that ends midterm 1 material. Midterm 1. This direction. Yeah. So, here's the deal. I was tempted. I was thinking about this last night, and I was tempted. Yeah, let's just not have chapter 2. I fear saying that because I'll get emails. Did you say that it wasn't going to be on there? I was thinking about where to end the material for the first midterm, and I thought it's better to have a little bit more on the first midterm because I think most students find overwhelming amount of material for midterm 2. Don't you think that? It usually ends up being that way. So that's why we're stopping at this point. It will actually make it easier for you for the rest of the quarter. When things start to get really intense. God, I didn't do anything. Did you see how that did that just right when I said intense? What does it mean? Okay. Let's talk about reactions of anhydride. Of course, this will not be on the test. So as we've seen, here's anhydrides right here. It's easy to go downhill. So we can easily convert an anhydride into an ester or carboxylic acid. We can also easily convert it into an amide. And that's because we have the energy diagram looking like this, where we have the second step is lower in energy here. Boom, 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 boom. Best leaving group is going to leave, and that accounts for the lower energy second step for that reaction. What we can't do, I got to stop emphasizing words here. Some things going on here. We can't do anhydride up to acid chloride. That would be an uphill reaction. And it would look like this. We have a large energy of activation for the first step and an even larger energy of activation for the second step, because if we're trying to make an acid chloride into an anhydride, we have to have a worse leaving group leave, and that's the problem. So that's why we have a really large energy of activation for that second step. All right, so we want to put a big X through that, right? That's not going to happen. Uphill doesn't happen. Unless you use forcing conditions or special reagents, and this is not one of them that we're going to be able to do that with. All right, so let's show why anhydride can't go to acid chloride. So you can see it from the energy diagram. You can also see it by actually doing the arrow pushing for this reaction. So chloride's going to attack one of the two carbonyls of the anhydride. Does not matter which. I will always have symmetrical anhydride, so you don't have to decide which carbonyl to attack. All right, and now we're going to draw our tetrahedral intermediate. Look at what we have and then make a decision. What's the best leaving group? Chloride ion. In order to go from an anhydride to an acid chloride, you have to have a worse leaving group leave, and that's not going to happen. So what is going to happen is these electrons are going to come down and kick chloride right back off. So it goes back to anhydride. All right, let's look at some more examples. Do you want me to include anhydrides on the test? I know. No. Okay, it is easy to go downhill. Let's look at some downhills here. Water. Water attacks an anhydride. Tetrahedral intermediate. And this reaction actually goes better when it has a little bit of acid catalyst in it, and you'll see kind of why here. Our best leaving group is water, which would reverse and go back to the starting material. So in this one, I'm going to deprotonate. And this reaction actually works better if you add a little bit of an acid or base catalyst. So it looks like this. If we deprotonate that first, now it's very clear what the best leaving group is. And that's what we're going to have leave. So this reaction will go without acid or base, but it works a lot better when you do use acid or base catalysis. And so now we definitely have our best leaving group is going to be here. That's our best leaving group. So electrons come down and we kick off the best leaving group. Then that leaves us with a carboxylic acid. Same thing with an amide. Notice we're using two equivalents here. Yeah. Deprotonate intramolecularly. You can protonate and deprotonate intermolecularly if it makes a 5 or 6 member transition state. So if you count all the atoms involved and you count 5 or 6, that can happen. But I don't believe we have that here. So it would be, so you're having this coming and grab that, yeah? 1, 2, 3, 4. 4 it can't reach. It has to be 5 or 6. Great question, by the way. All right, so let's look at the amide here. Also need two equivalents. Or one equivalent of this. And pyridine. So it depends. If you choose two equivalent, if it's a very inexpensive, cheap amine that you don't mind losing half of it. If it's an important amine, that's something that you've had to synthesize, you don't want to waste half of it. So you will use one equivalent of amine and one equivalent of pyridine. Yes? Yeah. No, it actually works without it. But as you can see, we have this one's a little bit different, and it actually helps it with. You don't have to write small amount of acid or base. Okay? Yeah.
And if you don't use a lot of water, will the reaction still work?
The reaction will go, but it will be incomplete. It's kind of like with the amide. Yeah. All right. So I'm not going to go through this one. This is going to look just like the previous example here. There's all your side products, in case Sapling asks for that. We want to keep track of that kind of stuff, which I don't usually have you do on the test. All right, so that's anhydrides. Questions on anhydrides? Anybody? Let's talk about reactions of esters in the last minute. Okay, so we already know what we can do here and what we can't do. So these guys, we can convert back and forth. It's a reversible reaction that we're going to have to drive. So ester, we can convert to a carboxylic acid, and we can convert a carboxylic acid to an ester. So we can, since we're talking about esters, we can easily go to the right. We can't go this way. Cross that out. We can't go this way. Cross that out, but we can easily go this way. So this will be easy. And these can't do. Can't go uphill. but we can go downhill easily. We'll talk more about this on Wednesday.